Hi, welcome back to Statistics and Analysis Week 5 tutorial. And today's topic is on bivariate distributions and correlations. So again, as usual, I like to list about a few uh, subtopics that we want to talk about. First is about conditional probability, quick revisit, right? Then we want to talk about an associated concept, conditional expectation or conditional expected value. Um, this will be written as P of example x equals to A given that y equals to B. Okay, and this will be example E of y when x is equal to 3 or given that x is equal to 3. Okay, and then we want to talk about covariance of x and y and its associated notion of correlation of x and y, also written as rho. Okay, all right. So first thing first, recall what is conditional probability of x equals to A given that y is equal to B. We did very extensive explanation and understanding of this being equal to the P of x equals to A, and right, if you are afraid of confusion, you can put a bracket, y equals to B divided by P of y equals to B. Because here we are dealing with probabilities and deriving the formulas, so we have no choice. We can't go by counting, and so we go by strictly the definition and the operations that are valid on probabilities. So this dividing by probability is very hard to find a meaning to. What do you mean by a probability divided by a probability? But thanks to the definition and we observe strictly, right, all the valid rules allowing for algebra to happen, we can have this. So this means when x is A and y is B, for example, when you're when a person, we randomly pick people, right? So that's random variable of the people's height and weight. So when a person's height is medium and the weight is large, right, then that would fulfill this condition. So if A is like medium, B is large, right? So then we sort of divide through by the probability of all the people who are uh, having large weights. So that's the um, way to think about it. Okay, and the idea of bivariate distribution means the presence of x and y, and this is looking somewhat similar because it's conditional probability, but somewhat different from what we have discussed in earlier video sessions on conditional probabilities, because back then we were just talking about um, uh, x and y or two different events, right? Or x is one random variable but two different events. Right now we have two random variables, x and y. So that's just a quick revision. And the associated expected operator, right? Expected value operator of y given x equals to 3. First thing first is that this 3 is just to not let you feel so fearful. So the 3 can be replaced by any number, any event. It can be 7, 3.5, just any number. So the result will still be generalizable. So given that x equals to 3 is a fact, find the weighted sum, weighted average of y. Now, the whole idea is essentially just applying the expected value operator over all values of x of y, right, weighted by the conditional probability. So the conditional part is outsourced to the probability. That's all. So y equals to all the valid values of y in y's sample space, right? Given that x equals to 3. So the conditional part of it can only be correctly interpreted in the conditional operator sense. And after that, it is just multiplied by the value of yi. Yeah, and of course we have yi because we are interested in finding the y value or the expected value of y. And likewise here. Yeah. Okay, so that's the basic idea. So let's try to work on an example. So for instance, y equals to 3 values, right? Nothing fanciful, but many enough to, make it not 1, not 2, but 3. So make it look like a distribution. So these values, we can actually give specific numbers to them. And I purposely choose 7, just so as to say that it can be any value, not necessarily odd numbers or consecutive numbers. Then we can say, okay, x is equals to 3. Given that x is equals to 3, so this is P of y equals to yi, given that x is equals to 3. Yeah, and we're kind of like already spilling over. And let's say the first number is 0.7, okay, 0.2, and 0.1. So how do we interpret this? This is essentially when, given that we know that, all right, already x is 3, when y is 1, the chance of seeing that is 0.7 because the y values haven't happened yet. So the chance of seeing y equals to 1, knowing that x is already 3, 0.7. The chance of seeing 3, 0.2, and 7, 0.1. So that's the idea here. And notice they add up to 1. Right? So they add up to 1, sum to 1, because given that x is 3, all possible occurrences of y being 1, 3, or 7 must be the entire population, right? Must be accounting for 100% of the occurrences. And that's why the probability has to add up to 1 in this conditional sense. Are you okay? All right. So to calculate the expected value, we can then just perform the operation. And since the probabilities are already known, right, so we can just directly calculate. So E of y, given that x is equal to 3, is going to be the product of the conditional probability, but it's already here. So the number calculation is actually very simple because the label has been shown here, which is exactly what we need. So 0.7 times 1 plus 0.2 times 3 plus 0.1 times 7. So this is 0.7, 0.6, 1.3, and then 0.7. So answer is 2. Is that right? 0.7, right? Then 0.6, 1.3, then 0.7, 2. Yeah. So the conditional expected value of y is 3. Notice that we don't write y equals to something because y has to be over the entire sample space of y. So everything, you cannot say expected value of y equals to something given that x equals to 3. But x can be anything. In fact, it can also be a range, like 1 less than equal to x less than equal to 3. So given that x is in this range, what's the expected value of y? That's also okay. That's also okay. Yeah, possible. Now, the reason why I have a little bit of gap here is to show you just a little bit of extension here so as to make it a 2-dimensional space. y. What does that mean? So let's say x equals to 2. Then we have p of y equals to yi, right? Given that x is equals to 2. And they can be different numbers. So for example, 0.3, 0.5, 0.2. Again, row-wise, it has to sum to 1. Yeah, but this is a different situation. X is 2. Before, x was 3. And of course, the y value probabilities will have some rearrangements, but the overall must add up to 100% of the occurrences. Yeah, and you can do the same, right? So to find out the expected value of y when x is equal to 2. And of course, the number will be different. Yeah, and so what it means here is that we want to understand, yeah, the probability of the distribution p of x comma y. And that's to say that as x may be low weight, high weight, right? Y can be short, medium, tall people, yeah, something like that. So you can think of it as maybe like t-shirt size, right? We have those numbers, yeah. So it's to describe short, medium, tall people, right? So 137. So the number is not just qualitative label, but also numerical, and you can calculate expected value. And what does it mean when we have these situations? So now what I want to do is to kind of reconstruct the probability values, right? So what that means is that I have a table, right? And x equals to 2, x equals to 3, and then of course the y values, y1 equals to 1, y2 equals to 3, y3 equals to 7. Yeah, and I want to say that when so this is the p of x y table. When x is 2, y is 1, what's the probability? And we can reconstruct it by first determining what is the probability of x equals to 3 and probability of x equals to 2. So regardless of y's values, what is the probability of x equals to 3? Now we cannot say it's 1 because this is the conditional probability. Sum of all the conditional probabilities for x equals to 3 must add up to 1. That's not to say what is the probability of x equals to 3 itself. Because remember, when we're talking about this, in the middle of talking about conditional probabilities, x equals 3 is already a fact. The probability is 1, it has occurred. So what happens to before, prior to x equals to 3 having occurred? What's the chance that we see x equals to 3? That's what we are talking about. So for its simplicity, suppose we do measurements or we do estimation and we just give it 0.5, right? You can change the numbers after you see what we're going to do with them. So let's say it's 0.5 and 0.5. In other words, the chance of seeing x equals to 3 is 0.5. Okay, and let's imagine what is happening here. P of y equals to yi, what equals to 1, given that, just take this example first. So P of y equals to 1, given that x equals to 3, right? We have to interpret it as P of y equals to 1 and, right, or comma, x is equals to 3, divided by P of x equals to 3. Right now, yeah? So therefore, if this is what we are after, the numerator is what we are after, what we do is we have this and we have this, we just multiply them together, right now. So now that we have this, right, this is the denominator. Like this. Right, and we have this as the numerator, the value. All we need to do is to multiply these two to get x equals to 3 and y equals to 1. So this must be the probability to be filled up here. Okay, so that's the ballpark plan. And we can just do a quick mental calculation. 0.7 times 0.5. right? I'm not going to write down until I use up all the space, which doesn't add much value, right? So 0.7 times 0.5, let me better verify with calculator. I think it's 0.35, but let's check. Okay, so 0.35. Okay, you get the idea. Now, once you get this idea, you certainly know how to continue, isn't it? Yeah, and you will then do 0.2, second column, times 0.5. Okay, and so that's 0.10, and 0.1 times 0.5, so 0.05. Yeah, so now it adds up to definitely 0.5, because if you ask p of x equals to 3, regardless of all the y values, that's what you do. You add them all up, right? Not, yeah. So I'm just showing you how you reverse derive, right? The joint probability space. We call this the joint probability of x and y. Joint in the sense of and. When x is this and y is that, both have not occurred yet. Both events, x equals to this and y equals to that, have not occurred yet. As opposed to conditional probabilities, right? Given y equals to b, we know that it's already the case. So same thing, let's do the quick calculation. 0.3 times the second 0.5, the p of x equals to 2.5. So 0.3 times 0.5, we get a 0.15. And 0.5 times 0.5, 0.25. 0.2 times 0.5, we get a 0.10. So this will be our joint probability table for x and y. And in some sense, this joint probability can also be visualized. Okay, so we can try to sketch something. I hope we can do that nicely without messing up. Okay, so let's try. Okay, so we go this way. Okay, so this is going to be our x equals to 2 and 3, right? So this will be like this, and we have 1, 3, and 7, like this. Okay, and the back extends upwards to 0.35 height, and this is the middle. So the 3 should be here, and then the 2 should be here. Okay, so we do reach this height. Like this. Just give me a moment to roughly estimate the height here. Okay, that's for this particular cell. Okay, next we have 0.1 and 0.05. So if this is 0.3, then 0.2, then 0.1. So roughly here, yeah, this is going to be our 0.1 height at the back, like this. So this is 0.10, right? And this will come down, okay, and it will share the floor here. Okay, and finally half of this, right, 0.05, that is going to be our third building, our third block. Okay, so that's to show the heights for these three. And then we can, of course, show 3, and this is 2, 1, so 2, 5 is here, and the 0.25, we show the 0.25 here. This is 0.25 height, and this is extending to the front. So to the front, and we are trying to see a bivariate distribution. We're trying to see it, and it can be seen because bivariate is two-dimensional, and we are having a 3D view of this two-dimensional table, right? So that's okay, possible, doable. Okay, so this is the 0.25 height projected onto the plane. Okay. Okay, and we have on the left side 0.15 and on the right 0.1. 0.1 is nice because it's just right here. So we can do this. So it comes to the front and it forms a little square here on top, right, on the rooftop. Good, and this is done. And then we have a 0.1 and a 5 roughly here. So this is 0.10 and this is 0.25, 0.2, 0.1, 15 should be around here. Okay, so we know this is going to be like this. You know, of course, I'm manually drawing it, not so accurate, but roughly, okay, roughly it is showing what it should be showing, the relative heights. And now I can kind of hide the line behind because we know it's going to be blocked. So that's the advantage. Okay, good. So if we emphasize the front lines, yeah, and you can see these are the front lines. Now then the so-called shape of it, the distribution shape, right, will be much more visible. And we can of course highlight the behind with something contrasting. Yeah, okay, so this is 0.25. Okay, all right. And you can have this. Now it becomes more visually distinct, right? Inviting our eyes to see more clearly. And then I'm not shading those blocked lines so that it will enhance the overall 3D effect, which I hope you will agree, right? Okay, so that is our very quickly, our very simple joint probability of x comma y, or you can say y comma x. So this is the joint distribution, because we can now see the shape, right, of y and x. Like this. Yeah. So this will be the kind of probability table that we are given in certain questions where they add up to 1. Yeah, the whole table adds up to 1. Notice this. Yeah, the whole table adds up to 1. Because these rows add up to 0.5, these rows add up to 0.5, they add up to 1. So the whole table adds up to 1. As opposed to this conditional probability table, like giving you the conditional probabilities of one instance at a time, x equals to 3, then x equals to 2, so that the row itself must add up to 1. So please be, on the lookout and ensure that you don't fall into misinterpretation like this. Okay, next, let's talk about correlation. So there are two kinds of correlation. There's a population and the sample. So for population, we will write the entire random variable itself, right? Correlation. And we typically also use rho to reflect this. So that is equal to, or is actually defined by covariance of xy. And of course, we use xy means we use the population version of covariance. And all of you know, right, that there is a population and a sample variance. And since we're using x itself, the whole random variable, this var always means population variance. And therefore, the var y is population variance for y. And then we take the square root to mean that the SD for x, the standard deviation, again, population standard deviation. All right, not a sample. So this is the definition. And we do have the sample version. The sample version is R. right? R is just R. We don't write a small chorale. We also don't use, you know, the capital letters. R is just R. And that's why you see a Greek letter, right? So Greek letters always refer to the population parameters. Now we want to talk about, of course, what is covariance. Covariance of x and y. Covariance of x and y will be therefore defined by correlation times the standard deviation of x, the standard deviation of y. Okay. But if we think back, right, if we revise back, recall that the variance of x, right, was the expected value of the square of the differences of the values from the mean value, like this, right? Then it is probably easier to think of covariance as a raw definition, also in terms of expected value. So expected value of, you see the variance is the square, right? Which means two copies of x minus e of x times together. And if we are to replace x with x and y, then it makes sense to say that we want the expected value of one copy is made up of x minus e of x. And so we multiply by not this again, but another copy is made up of y minus e of y itself. So that's the kind of raw calculation definition for covariance, right? So we cannot say correlation is defined by covariance divided by standard deviations, and then therefore covariance is correlation times standard deviation. But we can calculate using calculator, Excel, R, based on this. And if you're interested, you can of course try it out yourself, perhaps using the joint probability table. But what we want to talk about more here is that covariance, if you replace the y with x, sort of like covariance of x comma x, you find that it is x minus ex, x minus ex, which means bracket x minus ex square, which is back to variance. So it is easy to see that covariance of x and x is simply the variance of x. So you can think of variance of x as a special case of covariance of the random variable co-varying with itself. When I change, I am changing. All right, the other axis, which is me, changes. So it's like the random variable looks into the mirror, find the covariance of me and the mirror, and that is the variance. Yeah, that's an interesting kind of revelation. And of course, based on this, we can also get covariance of x comma y is rho. And to emphasize that this rho, this correlation, is for x and y, sometimes we put an xy there. All right, especially when v and w and other variables, random variables, are around, then we want to stress that, hey, look, this correlation is between x and y that we are talking about. And then we have the sigma of x, sigma of y. And that's not difficult to see because square root of var x is sigma x, just using the Greek notation, right? Square root of variance of y, standard deviation of y, population standard deviation of y. So if you bring them to the left, then it's just rho times sigma x, sigma y. So that's another nice equation or identity we can use. Next is covariance of a constant with a random variable is always 0. So constant as a entirety, that means if you repeat 3 infinite number of times as a random variable, yeah, because it occurs a lot, not one number, but infinitely many 3s, that constant random variable doesn't covary with any random variable. So anything that covaries with if you ask what's the covariance of x with 3 or any number, the answer is just 0. that is constant random variable. That means a random variable whose value is always fixed, right, is independent of any random variable. That can be said too. Okay. Of course, we are making use of this relationship. If x and y are independent, correlation between them is equals to 0. And this, if rho xy is 0, sigma x, sigma y, they are not 0, then definitely covariance has to be 0. Okay. The reverse in general is not necessarily true. So if I have some data, some distribution, some joint probabilities for x and y that ended up giving you a computed correlation of 0 or covariance of 0, it kind of might trick you to think that x and y are independent. All right. So, but when in fact they are not. It's like some magnetic forces are forcing the numbers to behave in a way that after calculation, your correlation, your covariance is 0. When in fact it's strongly non-independent. It's affected, it's pushed, it's coerced by the magnetic forces, right? That force the values the way they look, the way they are measured. However, there will be test questions, quiz questions, right? That may just say that which of the following shows that x and y are independent, right? So if they tell you some situations, right, then you might choose this as a sort of a introductory understanding, right? But then just realize that in general, the reverse is not true. Some situations you can say that, hey, the correlation is 0, so x and y likely are statistically independent, and that's true. All right. So more correctly is to say it is uncorrelated. So sometimes you might hear people saying, "Hey, I got the correlation of 0, so x and y are independent." Then another person posting a reply, such as on the Stack Exchange or Math Exchange, will say, sorry, correlation equals to 0 simply means x and y are uncorrelated. That means they produce a correlation of 0, but that does not imply that they are independent. So just think about that again. Okay, next we want to talk about the commutative property of covariance. Right, covariance, and as a result, correlation as well. If you swap x with y, y with x, covariance of xy becomes covariance of yx, and var x becomes var y becomes var x, and you times them together, no change in the denominator. But that's also true for covariance. So covariance, if you swap them, if you look at the definition, it's like you swap these two. You don't talk about x first, you talk about y first. So no effect at all. The answer is the same. So it is commutative. And commutative. Commutative. That means if you swap them, the answer is the same. And if we have a constant multiple of x, like ax, right, and by, recall last time when we say variance of 2x, we can take out the 2, but the 2 becomes a square, right? So it's 2 square variance of x. Here we are having two numbers, so it will not be a square b square. Instead, it will be ab. So we bring out the a, we bring out the b, much like the square becomes split into two copies, right? One occupied by y. So same thing here, the constant, each constant from x and y, they are extracted out to give you AB covariance of x comma y. Okay, so basically these are the most useful relationships all right, and the connections between covariance, correlation, and variance that you will need. And I will leave you with the screen, and that's the end for this particular session. Thank you, and see you in the next video session.